Hi, everybody. It's Professor Mitchell, and today we're looking at section 7.4 on exponential change and separable differential equations. In modeling many real-world situations, a quantity y increases or decreases at a rate proportional to its size at a given time t. Examples of such quantities include the size of a population, the amount of decaying radioactive material, and the temperature difference between a hot object and its surrounding medium. Such quantities are said to undergo exponential change. If the amount present at time t equals 0 is called y0, then we can find y as a function of t by solving the following initial value problem. The differential equation is dy dt equals k times y. So what that says in English is that the change in y with respect to time is proportional to y, which represents an amount. And the initial condition for this initial value problem is that y equals some number y0 when t equals 0. So y0 represents the initial amount. The solution of this initial value problem is y equals y0 times e to the kt. So this is one of those things that I can't resist showing you the details. Actually, I think this will be sort of a good warm-up for showing you what it's going to look like when we solve these differential equations. So let me switch over to my tablet. All right, here we go. So dy dt is equal to ky, and y equals y0 when t equals 0. So as you'll see, when we get into more examples, what we want to do with a differential equation like this is get all of one variable on one side and the other variable on the other side. So I'm going to get all of my y's on the left side, and I'm going to get all my t's on the right side. And the way I'm going to do that, and don't feel like you have to do this in one step, is I'm going to multiply both sides by dt over ky. All right, so what that's going to give me is dy over ky equals dt, right? Oh, I guess I could have left the k over on the right side. Right. Well, it doesn't matter. So now that I have the y's on one side and the t's on the other side, I am going to integrate both sides. All right, so the integral of dy over ky, just imagine putting this 1 over k out front. That's going to give me 1 over k times natural log absolute value y. Now, I know I'm supposed to write plus c there. Bear with me for just a second. We should have a plus c on one side and a plus c on the other side. Now, remember, the plus c represents an arbitrary constant. So I don't want you to think that if I wrote plus c on the left side and plus c on the right side, that I would then be able to cancel out the c's, all right? The plus c does not represent a specific number. It really represents any real number, okay? So when you're solving a differential equation like this, all you have to do is just put a plus c on one side. Now, I'm going to be a little official about this. I'm going to call this constant C1 for right now, because I'm going to go through a sequence of steps. And every time I do a certain thing, the value of the constant will change. In future problems, I won't be quite so sort of compulsive about it. All right. You'll see what I mean a little bit later. Okay, so now what I'm going to do is multiply both sides by k. So here's a good example of how you treat the plus c. The k's on that side are going to cancel and just leave me natural log absolute value y. If you distribute that k, what you would officially have is kt plus k times c1. But what is k times c1? It's just another constant. So I'm going to call it c2. All right, now, remember, we want to solve this thing for y. So the next thing I'm going to do is exponentiate both sides. So that's going to look like e to the power natural log absolute value y equals e to the power kt plus c2. All right, and maybe I had better rewrite that equation at the top of the next page. E to the power natural log absolute value y equals e to the power kt plus c2. All right, so what we have on the left side is the absolute value of y. And now what we have on the right side, using my property, one of my properties of the exponential function e to the x, you can write this thing as e to the power c2 times e to the power kt. But what is e to the power? Actually, I'm not quite ready for that yet. I have absolute value y equals e to the c2 times e to the kt. So if I want to make that just about y, what that would say is that y is either the positive or negative plus or minus e to the c2 times e to the kt. Okay, but what is plus or minus e to the power c2? It's just another constant. And you know what? Now I'm going to call it c. Again, in future problems, I'm not going to be quite so compulsive about it. This is really the way you should do it. But you'll probably see me just calling my constant c at each step, understanding that the particular value of c would change, but that really doesn't matter. Okay, so this is the general solution to the differential equation dy dt equals k times y. But remember, we had an initial condition. The value of y at time 0 was some number y0, okay? So on the one hand, y at 0 is y0. On the other hand, y at 0 is c times e to the power k times 0. And what is e to the k times 0? Well, it's just e to the 0. E to the 0 is 1. So we have found that this mystery constant c is just the initial amount y0. So taking this equation, we now have y is equal to y0 times e to the kt. All right, so that's one of those things I couldn't resist showing you. And again, it's good practice for what we're going to be doing here pretty soon. All right, so let me go back to the presentation. There was a little note at the bottom of this slide. Quantities changing in this way are said to undergo exponential growth if k is greater than 0, and exponential decay if k is less than 0. The number k is called the rate constant of the change. All right, so the only kind of differential equations we're going to be dealing with in this class, and we only do differential equations for a very short amount of time. Probably in about 2 semesters from now, you'll be taking a differential equations class, for example, Math 6 here at our college, where you will learn to solve a whole variety of different types of differential equations. The only kind that we deal with in this class are the easiest kind, which are separable differential equations. Exponential change is modeled by a differential equation of the form dy dx equals ky for some non-zero constant k. So that's the kind we were just looking at. More generally, suppose we have a differential equation of the form dy dx equals f of x and y, a function of x and y, where f is a function of both the independent and dependent variables. That equation is called separable if f can be expressed as a product of a function of x and a function of y. So that differential equation would have the form dy dx equals g of x times h of y. When we rewrite this equation in the form dy dx equals g of x over little h of y, so they've renamed, you can see here how they've renamed this function. Its differential form allows us to collect all y terms with dy and all x terms with dx. So you saw how we did that just a moment ago. And then it looks like h of y dy equals g of x dx. Now we simply integrate both sides of this equation. And after completing the integrations, we obtain the solution y. It says defined implicitly as a function of x. That's sort of the worst case scenario. The best case scenario is that you can actually solve the resulting equation for y, like we were able to do in the last problem, and like I think I'll be able to do in both of these examples. So let's go back to the tablet and look at these examples. All right, so our first example is dy dx equals 3x squared times e to the negative y. Notice that it's two separate functions. Sorry, I keep getting a message here. Hopefully this recording is still happening. All right. So you have 3x squared times e to the negative y. So this will be very easy to separate. And again, don't feel like you have to do this all in one step. I will go ahead and do it in one step because I kind of gave it a little bit of thought beforehand. So what I'm going to do with this one is multiply both sides by e to the y dx, because e to the y is the reciprocal of e to the negative y. All right, so on the left side, the dx's are going to drop out, and on the right side, e to the negative y will cancel e to the y. So what we have is e to the y dy equals 3x squared dx. All right, so now I'm ready to integrate both sides. All right, so on the left-hand side, I have e to the y. Remember, you don't need the plus c, you only need to put that on one side. Equals the integral of 3x squared dx is x cubed plus c, right? And now to solve this equation for y, just take the natural log of both sides. Natural log of e to the y equals natural log x cubed plus c. All right, so the general solution of this differential equation is y equals the natural log of x cubed plus c with the plus c inside the natural log. That might look a little strange. Okay, but that's what it is. All right, next example. So in this example, we actually have to do a little bit of work to separate the x's from the y's. So how are we going to do that? Well, maybe it's been a while since you've had to do this kind of factoring, but xy plus 3x minus 2y minus 6 can be factored by grouping. Do you remember how that works? Take these first two terms, you can factor out an x, leaves you y plus 3. And then if you factor a -2 out of those two terms, you're left with y plus 3. Now I have a common factor, y plus 3. And this thing will factor into x minus 2 times y plus 3. All right, so very easy to separate that. I am going to multiply both sides by dx over y plus 3. So dx's will drop out on this side, y plus 3 will drop out on that side. And that'll leave me with dy over y plus 3 equals x minus 2 dx. All right, so we got all our y's on one side, all our x's on the other side. We are ready to integrate both sides. All right, so on the left side, we have natural log, absolute value y plus 3 equals the integral of x is x squared over 2. The integral of minus 2 is minus 2x. And we do need to put a plus c somewhere. I'll put it there. This reminds me just a little bit of the, dy dt equals k times y that we did at the beginning. All right, so the next step to solving this thing for y is we're going to exponentiate both sides. I remember a few years ago, I had I think it was a pre-calc student who used to say e both sides. He used e as a verb. I thought that was kind of funny, and I think we adopted it for that class. Technically, e is not a verb, but that's okay. Maybe it should be. All right, so going over to the next slide, I'm not really going to do a whole lot with the right-hand side. But the left-hand side, of course, is going to become absolute value y plus 3. And that's equal to e to the power x squared over 2 minus 2x plus c. All right, so remember how in that first problem, I broke off that c like this using that property of the exponential function. You can write this as e to the c times e to the power x squared over 2 minus 2x. And then that e to the, well, I'm not ready for that yet. All right. Next thing I'm going to do is get rid of the absolute value. If the absolute value of y plus 3 is equal to, let's just call it that thing, then y plus 3 has to be the plus or minus of that thing. And what is plus or minus e to the c? It's just another c. So notice I'm being kind of unofficial this time. I'm just reusing the letter c. All right, it does represent a different number, but that doesn't matter because c can be any real number, right? All right, so now the only thing left to do is get rid of this plus 3 here, and the general solution of this differential equation is going to be y equals c times e to the power x squared over 2 minus 2x minus 3. Done. All right, back to the presentation. Oops. Okay. An example of unlimited population growth. A colony of bacteria is grown under ideal conditions in a laboratory so that the population increases exponentially with time. At the end of 3 hours, there are 10,000 bacteria, and at the end of 5 hours, there are 40,000 bacteria. And the question is, how many bacteria were present initially? And this is technically a pre-calc problem, really. All right, so back to the tablet. Not going to use any calculus in this problem. We did use calculus to derive this formula. Okay. All right, so remember it said that when t is 3, y is 10,000. And it said when t is 5, y is 40,000. Now, I believe with these particular numbers, there is probably a gimmick to this problem. So I just want to go out on record saying that I recognize that. I could very easily tweak these numbers and then the gimmick would not really work. But what I'm about to show you will always work. All right. And we want to find y0. Okay. So substituting those values, t equals 3 and y equals 10,000 into our equation, we get 10,000 equals y0 times e to the 3k, right? Because we're replacing t with 3. Excuse me. And doing the same thing with the other set of numbers, we get 40,000 equals y0 times e to the 5k. Now, if you solve both of these equations for y0, let's just do it. On the one hand, this equation says y0 equals 10,000 over e to the 3k. This equation says y0 equals 40,000 over e to the 5k. Both of those things are equal to y0, and so they have to be equal to each other. 10,000 over e to the 3k has to equal 40,000 over e to the 5k. All right, so cross multiplying, we get that 10,000 times e to the 5k is equal to 40,000 times e to the 3k. All right, so let's try to solve this thing for k. If we divide both sides by 10,000, that'll get rid of this, and I'll make this a 4. And if we also divide both sides by e to the 3k, that'll get rid of this. And on the left side, what we will have is e to the power 5k minus 3k is 2k, right? So we have e to the 2k equals 4. And if we take the natural log of both sides, that means that 2k is equal to the natural log of 4, which means that k is 1/2 natural log 4. Now, I want to be very careful how I say this because I don't want you to think the right thing for the wrong reason. 1/2 natural log 4 does simplify, but this is the reason it simplifies to what it does. I'm going to show a ridiculous amount of work here. All right. So k is equal to natural log 2. So now, let's just look back here for 1 second. We had not just one, but two different expressions that explain how y0 relates to k, for example, this one. And now we know that k is equal to natural log 2. So we have that y0 is equal to 10,000 divided by e to the power 3 natural log 2, which happens to be 1,250. If there were 10,000 bacteria at 3 hours and there were 40,000 bacteria at 5 hours, we must have started with 1,250 bacteria.